For this lesson, we're going to be continuing with our review of some material from a previous course. So we're going to take a look at the sine law and cosine law. If you need a deeper refresher than what I'm going to provide in this video, then I would encourage you to go take a look at my notes for the grade 10 course where I cover the sine law and cosine law in a bit more detail. I also do derivations for each of them to show where they come from, and there are more worked examples. Also, it's going to sound like a crazy thing to do, but I would also strongly recommend you go and search other YouTube channels. Mathematics at this level is covered by hundreds, if not thousands, of other teachers and just amateurs who want to try to help people understand. So you should absolutely avail yourself of these other options as well. So let's go ahead and get into it. When we want to deal with the sine law and cosine law, that's going to be when we are asked very specific questions dealing with non-right triangles. If you have a question that is dealing with a right triangle, you should be using right angle trigonometry. Okay, so keep that in mind. A lot of students, when they learn the sine law and cosine law, I make the equivalent analogy to the general quadratic formula. They have maybe something that's a little bit easier to remember, or it's a little bit more convenient, and so they treat it like just the one tool that they can go to all the time. And it's my experience that this is particularly applicable to the sine law. If you are using the sine law and any of these angles are 90 degrees, you're not really using it correctly. Will it work? Yes. But should you be doing it that way? No, you should not. And so, should you expect to receive full credit for your work? I would argue, as a math teacher, that again, no, you should not. One of the things you're trying to do here is learn the different tools and use them appropriately. It's not all about getting the right answer. The right answer is important, and if this is the only way you can get the right answer, okay, but it's not the only way you should be doing this. Okay, little speech is over. When you're using the sine law is one of the few relationships that we discuss in class that is expressed this way, which is with multiple equal signs. The sine law talks about the ratio of the angle to the opposite side, and in particular, the ratio of the sine of the angle to the opposite side. For any triangle, the ratio of the angles to the opposite sides are all going to be equal. So if A is a large angle, that means the side A will be a large side. If B is a small angle, that means side B will be a small side. And so that ratio results in this equality. When you're solving a sine law problem, what you want to do is you want to find a pair of these ratios where you have 3 out of 4 are known, okay, and 1 unknown. That's what we're going for. We can only solve an equation. If we have a single equation, we can solve it for 1 unknown. So you're going to want to go through these, figure out what you have, what you don't have, and solve it appropriately. Sometimes the thing we're solving for may be in the numerator or denominator. So it turns out that this set of equivalent expressions or ratios, you can just flip those over for another version of the sine law. So if you're solving for the sides, you might want to use this version. If you're solving for the angles, you might want to use this version. Either will work. It's just a matter of convenience. It's usually more convenient to have the thing that you're solving for in the numerator rather than the denominator. It's one less mistake to make. The cosine law, it's a very similar idea. So once again, we have a non-right triangle. The same advice, the same rule applies. If you have a right angle triangle, if you have 90 degrees, you should not be using either of these two formulas. These two formulas are equivalent expressions, but they're expressed quite differently. The cosine law relates the square of one side to the squares of the other side. So this part looks a lot like Pythagorean. Okay, that part looks a lot like the Pythagorean theorem. And then we have this extra part. And of course, the reason why we have to have that extra part is because it's not a right triangle. The Pythagorean theorem only applies to a right triangle. So that being the case, we've got this form, which I consider to be kind of the standard relationship for the cosine law. And then we have basically an algebraic manipulation of this first one. So all you really need is this one. But if you need to know an angle instead, then if we're interested in cosine of A, then what I'm going to do first is I'm going to take this whole piece and I'm going to move it to the left side, and I'll take the A squared and move it to the right side. So I end up with 2bc equals b squared plus c squared minus a squared. And if I do that, now I missed one very important thing here. I'm going to just rewrite that. So let's try again. 2bc, and don't forget the fact that it's also got a cosine of capital A, which is the angle A. And now I can write that the cosine of the angle A is b squared plus c squared minus a squared, all divided by the 2bc that was the coefficient for cosine A. And of course, that's just my sloppier version of this nicely computer-generated version. So long as you remember this first one, you can always change into the second one. Now, what are the conditions? Each of these equations relates to various angles. In this case, I've labeled them A, B, and C, and various sides A, B, and C. So how does the configuration of the triangle that we're given affect whether we should use the sine law or cosine law? And there are some rules of thumb. You can figure these things out for any triangle. You can just write out the sine law and do check marks where you have knowns and X's where you have unknowns. You could write out the cosine law and do check marks where you have knowns and X's where you have unknowns. And your goal is you always want 3 out of 4. Right? If you have 3 out of 4 knowns, then that means you have one unknown, and that means you can solve. Or actually, rather than saying 3 out of 4, that's for sine law. What you want when you form your equation is one unknown. Now, there are these rules to help us, so we don't have to write out those equations and check our knowns and unknowns and with check marks and X's. If you have two sides that are next to each other, and if you think about a triangle, if you know two of the sides, then that means you have two sides next to each other. If you have two sides next to each other and then an angle, that is, if you imagine kind of traveling around, if I start from here, there's my first side, side 1. I get to here, there's side 2, and then I get to here, that's angle 1. Side, side, angle. Whereas if I do this one, now in order to go in the order of things that I have here, I have side 1, angle 1, angle 2. This one is side, angle, angle. So if you have either of these two configurations, your knowns and unknowns are going to lend themselves to using the sine law. Here's another one. In this case, the direction I'm choosing is just to avoid places where I have nothing. So here I have side 1, and then the next thing I meet is angle 1, and then the last thing I meet is, it's not angle, it is side 2. And so in this case, side, angle, side. If I have side, angle, side, I use the cosine law. And then finally, give myself a little bit more room here, I can start anywhere with here, of course, and I go around, and I have side 1, side 2, side 3, and so the appropriate thing to use there is once again cosine law, because I have side, side, side. Using cosine law with side, 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 well, I have the 3 sides which are known, so the only unknowns are angles, so I can use this to find any angle. So should you memorize this? I would say no. But should you be thinking of this and referring back to this as you work through your problems? I would say yes. Eventually you get to the point where even just drawing out a quick sketch like this might be enough. So maybe you never memorize it, but you get comfortable enough with the process that you can reproduce this quite easily. All right, let's go ahead and start to do some work. I haven't made these problems particularly challenging. They're just solid review problems for using sine law or cosine law. So let's take a look in this case. What information, first of all, do I have? I'm being asked to solve for this angle theta. That's quite clear. But that doesn't mean that I can always go directly to my solution. So in this case, let's see. I am going to start here and start to travel around this way because there is side 1, there is side 2, and then I have angle 1. This is a side-side angle situation, which, if you remember that table, that would be sine law. If you're not sure about that table, then you can, I'm going to show you kind of the longer way to do this, which is certainly perfectly reliable. Since we're interested in an angle, let me go ahead and write this. First of all, I'm just going to write the standard form, which is sine A over A equals sine B over B equals sine C over C. So, of course, this is assuming A, B, and C for the vertices, which would be perfectly reasonable. And you know what? Why don't I go ahead and label that A, B, and C, which means the sides, this would be side A, over here would be side B, and over here would be side C. So now let's take a look at what we know and what we don't know. Do we know the angle A? No, we don't know the angle A, and we specifically want to know the angle A. Do we know the side A? Yes, we do. Do we know the angle B? We do not know the angle B, and we're not interested in the angle B, so I'm going to put an X there. Do we know the side B? We don't know the side B, and we're not interested in the side B, at least not yet. It's not stated in the question, so I put an X there. Do we know the angle C? Yes, we do. Do we know the side C? Yes, we do. So I can now take any pair of these, and so in this case, if I make my equation out of those ones, I have one unknown and 3 knowns. I can solve this. So this is going to become the sine of, instead of A, I'm going to use the angle theta, since that's the variable that was given. I have to make sure my units are all the same because I'm not going to write units in my equation. So I take a double check of my system here. Side A is 75 centimeters, which matches units with side C, so that's fine. Then I do the sine of angle C, which is 52 degrees, divided by the side C, which is 100. If you're good at your algebra and cross multiplying, you could probably go straight to your answer here, but I'm going to do it in 2 steps. So I am going to use cross multiplication, and so I end up with 100 sine theta is equal to 75 sine 52 degrees. One of the things you'll notice, or maybe you've already noticed with my videos, is that I prefer to do most of my algebra, or as much of my algebra as possible, before I go to a calculator. So I'm not going to calculate this yet. I'm actually going to isolate completely for sine theta, which becomes 75 sine 52 degrees over 100. Let's clean up that letter S. And only now would I bother going to my calculator. Since this is a final answer, I'm not using this value of theta for anything else, then I can go ahead and round my answer here. I'm going to round it to 1 decimal place since nothing is specified. So I do 75 sine of 52 divided by 100. And I'm going to write it, even though I'm going to keep this in my calculator. So this is going to end up being the inverse sine of approximately 0.5910. Now, I'm not doing my math using just these 4 digits. This is still in my calculator. I just wanted to put that there in case anybody's also checking themselves. So I'm going to take my inverse sine of my answer with all the digits intact, and I end up with an answer of 36.2 degrees. And I think I was clever in this case, but I wish I was this clever in all cases, which is that's not what I wanted to do. This should not be grouped. Let's ungroup that. And now I can move that, and I have my answer hidden in behind there. And so I can see that my answer is actually theta is equal to 36.2 degrees. Okay, find the length of side C. So I'm going to do the same thing again, except for in this case, I'm going to first of all, let's take a look. So starting from here, going this way, I have side 1, I have angle 1, and I have side 2. So I have side, angle, side. So what does side, angle, side say I'm supposed to use? Now, you either remember that, or you go back and you look at that diagram, or you can work it out. You can write out your equations, and you can just check off what do I have and what do I not have. It turns out side, angle, side is where you're going to use the cosine law. So side, angle, side lets me use the cosine law, and in this case, this is actually an important point. When you use the cosine law for side, angle, side, this is going to let you find the side across from the known angle. And that's very important because you might not always want what these equations are going to give you, but what these equations give you is all that you can get out of the triangle to start. So sometimes you might have to do this in 2 steps. But since we're focusing on review here, I've given you another 1-step problem. The general form of the cosine law, at least as I've got it written right now in our notes, is a squared equals b squared plus c squared minus 2bc cosine of a. But if you take a look at the lettering here, this triangle happens to also be labeled ABC. You should not be changing the labels to match this equation. You should be modifying this equation to match your situation. So in our case, this is side A, this is side B, and this angle we have here is angle C, which the side is already properly labeled as C. So now let's rewrite this equation. If this relationship is true, that means that c squared must be equal to the sum of the squares of the other 2 sides, a squared plus b squared, minus 2ab cosine, and the angle here matches this side, which means side C must have angle C. Now you can see I've done a little embellishment here just to try to distinguish between lowercase c and uppercase c. This one is full size, this one is only half size. If that doesn't work for you, you should feel free to label this maybe theta or something like that. I think that we can tell the difference for this one line. I'm going to replace this with a number in a moment, but make sure that you are being mindful of the clarity in your expressions. So c squared equals a squared is going to be 5.9 squared plus b squared, which is 5 squared, minus 2 times 5.9 times 5 times the cosine of this angle, 50 degrees. Now this is a lot to put in your calculator, so your calculator skills have to be good enough that you can do this without making any kind of significant error. So the first thing I'm going to do is calculate c squared, but I always keep everything in my calculator. So it's 5.9 squared plus 5 squared is just 25, minus 2 times 5.9 times 5 times the cosine of 50 degrees. Make sure your calculator's in degree mode. And so I end up here with c squared approximately equal to 21.8855. Now I'm not using that. 4 decimal places is going to be fine because I'm interested in a final answer which I'm going to round. But understand I'm keeping all of my results in my calculator until I get to my final answer. 4.7 is my approximate length. And since we don't have any units here, this is actually sufficient for a final answer. And there is the correct answer. C is equal to 4.7. I hope I've done this for all of them. That would be great. And I can already tell that I haven't done this for all of them because there's no little magic circle for me to take away there. Okay, this one, I'm not going to do a drawing around this, but you can see, what do I have? I have side, side, side. And side, side, side is cosine law. And if all I have are sides, then of course I'm going to find an angle. So once again, the standard form of cosine law, what I've got written in our notes, b squared plus c squared minus 2bc over the cosine of a. This is the form that is useful for solving for a side, but we already have our sides. So we might actually want to make use of the angle form, which we can either remember or we can manipulate this algebraically into the form cosine of a is equal to b squared plus c squared minus a squared over 2bc. And now I'm going to convert this. You should not be changing. This triangle is labeled J, K, and L, which means the side J is here, the side K is here, the side L is here. I should re-express this in terms of the angle K. So the cosine of capital K is equal to, well, b squared and c squared are just the sides that are not this. So what is not K? That would be J squared plus L squared minus the side K squared over 2JL. You need to be able to do this manipulation. Cosine of capital K is equal to J squared is going to be 2 squared plus K squared is 5 squared minus L squared, which is 6 squared. But I did that wrong, didn't I? It's supposed to be J squared, which is 2 squared, plus L squared, which is 6 squared, minus K squared, which is minus 5 squared. 2 times J, which is 2, times L, which is 6. You could do some simplification here if you wanted to, or you can go straight to your calculator. It's up to you. Since these numbers are all integers, wouldn't be the worst idea. So I'll just take an extra couple of lines. 4 plus 36 minus 25 over 24. Now, if your mental arithmetic is not good, then it might be a better idea for you to go straight to your calculator. If you're going to go straight to your calculator, remember that you have to use brackets to impose order of operations on these things. Cosine of the angle K, that's going to be 40 minus 25, which is 15 over 24, which means K is the inverse cosine of this thing. So inverse cosine of 15 divided by 24, and that equals 51.3 degrees. And since I don't have any more calculations to do in this case, then that would be fine. Now I notice that the angle here is actually labeled as theta. So it wouldn't have been the worst idea in the world. If you did this with K's, I think that would be valid because the vertex is labeled as K. But we could also have done this all in terms of theta. When a vertex is labeled, I don't want you relabeling the vertex. But if you decide you want to put variables in there, there's nothing wrong with that. I believe this is our last example. It wants us to solve for the side length y. So in this case, and I think I am going to go back to my drawing, I start here and go around. This would be angle 1 where I started. Then it hits angle 2. Then it hits, well, side 3. I should call that side 1. But the point here is we have a slightly cruder form, angle, angle, side. No, it's not a crude form. I was thinking it spelled something else. We have angle, angle, side, or side, angle, angle. So we have two angles here, and there's actually a pretty big clue there. Cosine law, there's no room in the cosine law for more than one angle. So this one is actually a sine law. So sometimes you can actually apply just a little bit of common sense there. This is a sine law. What are we interested in? We're interested in a side. So now let's do this one as if we want to save a little bit of time. Maybe you're quite comfortable with the sine law. So what would that look like? You wouldn't do this drawing. You would do that in your head. And actually, I'm going to need to label this. So let's call this, well, since I already have a side called y, how about we match that up? So let's put this vertex as capital Y. So maybe it makes sense to call this capital X and this side X, and this capital Z, which would make this side Z. See if I can make that capital Z a little more distinctive. So now let's go straight to the sine law on this. We're interested in side lengths, so I'm going to write x over the sine of x is equal to y over the sine of capital Y is equal to z over the sine of capital Z. And let's go through and see what we have. Do we know the side x? No. Do we want the side x? No. So I'm going to put a little cross next to it. What about the angle x? Yes, we have the angle x. Do we know the side y? No. Do we want the side y? Yes, we do. So I'm going to put a question mark there. Do we know the angle y? No, we don't. Do we know the side z? Yes, we do. Do we know the angle z? Yes, we do. So if you take a look at this, there's no grouping I can make that will only have one unknown. But since I really want this angle, this side length y, the next most important thing is going to be this angle y. So I'm going to change this from being an x into being something I need to find. But to find the angle y is actually quite easy, because I can just say that x plus y plus z, since they are in a triangle, they have to add up to 180 degrees. So that means that the angle y must be equal to 180 degrees minus the angle x, which is 48 degrees, minus the angle z, which is 52 degrees. 48 and 52 actually add up to 100, so the angle y is 180 minus 100, which is equal to 80 degrees. As you can see, this diagram is not even remotely drawn to scale, because this angle looks like it's probably the smallest in the triangle, but that's not realistic at all. You don't trust the diagrams to give you a very good representation of the actual situation. So now that we have the angle y is 80 degrees, we can make use of this grouping, because now I have the angle y, and from there I can now write that y divided by, what is the sine of the angle y? That's the sine of 80 degrees, is equal to z, the length of z is 100, over the sine of z, which is 52 degrees. As I stated in an earlier question, I prefer to do my algebra first. In this case, rather than do a full cross multiplication, I'm only going to multiply, basically I'm going to multiply by sine 80 on both sides. That gives me y equals, and now I end up with 100 sine 80 degrees divided by the sine of 52 degrees. And I can go straight to my answer now. If I'm careful with my calculator work, I can do 100 sine 80 and divide that by the sine of 52, and I end up with 124 point, actually it's 0.9739 rounded to 4 decimal places, but I want just to 1 decimal place. So this 7 would round this 9 up to a 0. So this actually rounded to 1 decimal place is 125.0. I notice that there are units here, so therefore y equals 125.0 centimeters is my final answer. Okay, that's it. So I basically gave you one example of each of the types from sine law and cosine law. We've got some, these are the basics, questions 1 through 3. So if you're still feeling some rust going into this review, you might want to tackle those first, and then you can get on to the questions that are a little bit more substantial.